Yeah, that said, the man of the hour really is Edson Ito here, our presenter today. Thanks, Edson, for joining. Edson's with Sumitomo Chemical, um, very experienced in the high performance engineering polymers kind of space, electronics, medical, automotive, kind of all over the place with LCP certainly, and kind of other similar super high performance materials. But very excited to have him today. You know, Edson's got about 30 years experience, I believe, right, Edson?
About that.
About give or take. I don't want to date you, but yeah, give or take 30 years here, and most of that, if not all that, in the LCP world. So, you know, very excited to have him. I believe he comes from a material science with a focus in polymerization background as well. So certainly an expert. So Edson, thanks for joining. I will kick it over to you in a second. But I think real quick, Weston wants to maybe go through future webinars and explain the Q&A. So go ahead, Weston. Thanks.
Excellent. Thanks, Bennett. Yeah, so as Bennett mentioned, this is number 14 in the Sodick series. Coming up here in a couple weeks, we have Kistler with their piezo sensors. Following that up is going to be in the new year here in 2021. We're going to kick it off with extreme molding, followed by Techmer PM, and then great new technology coming out from KPM Analytics. So we want to hit those as well. We'll try to keep the list updated here each couple of weeks that we sit in front of you guys. As Bennett mentioned, we'll try to hold the Q&A until the end. What we'll have you do is type in either the chat function or your Q&A function on the lower right-hand side of your screen there. Send those into the host. I'll compile that list, and as Edson is finished with his presentation today, we'll go ahead and fire those questions at him and let him spend a little bit of time on each one for you. I guess with that, Edson, it's your time, man. Go ahead.
Oh, no, thank you. Thank you very much. And again, I mean, I think first of all, thank you for the Sodick team, Len, Bennett, Weston, to help us to create this incredible platform to be able to share a little bit of our, I would say, knowledge and experience, and help a little bit on the whole supply chain coming from the raw material to the sophisticated software that goes behind the scene to make some of the parts coming alive together. So today we'll talk a little bit about liquid crystal polymer, and one of the reasons that we thought that was interesting, you know, a couple months ago when I was working to get my presentation on the way, I saw this quick poll that Bennett put together and was discussing about, you know, critical materials and understand, you know, the difficulties in some of them. And to my surprise, I end up seeing LCP there. And in certain ways, I believe that that comes from the part of not understanding really well certain behaviors that this material present. So I think in discussion with the Sodick team, we thought it was a good time to get some presentations about LCP. And so we can explain a little bit more, clarify certain questions about the usage and the behavior that LCP does have. And then try to see if we can take LCP from the naughty list for the end of the year, okay? Today, we'll talk a little bit about, you know, the overall Sumitomo Chemical organization, and then we'll jump pretty quick to discussing about SumikaSuper LCP and these major attributes, and then how we can take advantage of some of those polymer behavior that we've been discussing. And then we will close with quick information about how we do some simulation to understand the overall perspective of a cost per part. So just to touch base a little bit on Sumitomo. Sumitomo Chemical is a very large conglomerate of companies. So we have over 218 subsidiaries around the world with more than 30,000 employees spread throughout the world too. And, you know, different areas for developments and R&D. and it is a company with more than 100 years of in the market. We start from the fertilizer side, end up creating different usage for different chemical products, and end up with this huge organization. Overall, the revenue of the company is about $21 billion in 2019. We are organized under 5 different business groups. So going from the very traditional petrochemical, commodity type of plastics and polypropylene and olefinics to high-end pharmaceutical, agriculture, chemistry that does try to improve on the quality of life and improve on production from the production standpoint and in the agriculture side. And the division that the engineering thermoplastic belongs, it is under the energy and functional materials, which represent about 12% of the overall revenue from Sumitomo Chemical. Under the engineering functional materials, we have a couple different other products that are not related to thermoplastics. So going from additives that are used in rubber technology to alumina for electronics and certain components for lithium-ion batteries. But the main part, it is our division that handles the thermoplastic, which is the Advanced Polymer Division. Under that organization, we are responsible for the SumikaSuper LCP, the SumikaSuper E101, and we'll talk a little bit about that. SumikaXL PES, which it is amorphous material, but very high temperature performance one. Sumiploy, it is a group of different polymers that can be using LCP, PES, or PEEK to develop a very unique and specialized formulations for example, for tribological applications where you require a very low wear performance. And we also handle thermoset polymers like Sumi epoxy and polymers additives as Igerabond that are used in compounding for modifications of polymer behavior. One thing that I want to highlight too is the commitment of our organization for social employment, environmental responsibility. So we do spend a lot of time and a lot of effort to keep the organization striving from that perspective. And I think it was a very, very important recognition that we received this year was the Gold Award from the EcoVadis organization. So this represents the top 5% of all the chemical industries and different organizations throughout the world that are working to bring innovations and taking the technology to make it our life more sustainable and our future more sustainable. So that's one, I think, important side that we've been spending a lot of time, and especially, if you think about the chemical industry side, I think we have a very, very strong responsibility to keep that efforts going forward. From the Advanced Polymer Division side, we are pretty well distributed around the world. So with the main office in Tokyo, Japan, we do have offices in China, in Shanghai, in Korea, and Seoul. To cover the southeast portion, an office based in Singapore. And then in Europe, we cover through our Belgian organization. And in the US, we are based down in Phoenix, Arizona. This is our facility in Phoenix, Arizona. So under this headquarters, we cover more than one department. So part of the organization, it is for the IT-related products. And then the second part, it is the energy functional materials, as I described it before. And that's one of the reasons that in terms of production, we have one part of the facility organized to handle grinding for specialty materials for composites, and also all the administrative part for our APD group. but at the same time, we have production of wafers and technology for semiconductor used in solar energy, VC cells, and LEDs, for example. So it's kind of broad organization over in Phoenix, but we have a pretty good, I think, organization to cover different parts of these kind of a more high-end electronics to the consumer electronics side. So we'll jump now to our SumikaSuper LCP. This is our brand for liquid crystal polymer. It's one of the oldest material or oldest LCP in the marketplace. It's being produced since 1979. So has a long history of different type of formulations and different type of technologies involved on that. And that's the reason that when you look into this chart, where we describe all the different polymers available, or kind of the different type of polymers available, the LCPs will sit on the top of this chart. So it has a very high thermal performance compared to the other, traditional engineering thermoplastics, which will be here in the middle, or the commodity thermoplastics. Each color represents a different formulation, and different between those different families or series are their thermal performance. So you can see by the chart here, they will have different thermal performance and also utilizations that would be allowed by those performance. To understand a little bit about liquid crystal polymer, I think we need to step back a little bit to understand why the material behaves the way that it behaves. So if you think about the traditional semi-crystalline material, when you go to the molting stage, the molecules have so much energy that they can get in a very random position. Once they start to solidify, it takes a lot of energy to organize back to those crystalline domains and then start to taking form of those semi-crystalline structure. In liquid crystal polymer, even when you are in the molting stage, those rod type of structure still roughly very well organized. So when you are moving towards a solid phase, it doesn't take a lot of energy to organize back to a very structural form. So that would define a lot of, in terms of the cycle time that you will see that it is super low. The specific heat or the energy necessary to organize to solidify, it's very, very small. So compared to the crystalline that it takes a lot of energy to reorganize, we don't need that. So that's why when you do injection molding parts in liquid crystal polymer, you will see cycle times kind of on 5 seconds, 10 seconds, very, very short cycle times compared to the traditional semi-crystalline materials. And part of that structure will define the other part of those attributes that LCP will carry around. So this liquid crystal structure will define, the high flow side, the very good mechanical modulus that you will see in this product, the low mold shrinkage part, and the aromatic part of the chemistry of the structure will define the thermal performance. So this will help us to get the very high thermal performance behavior of this material, low outgassing, the inherent flame retardancy. So in other words, we don't need to add any additives to make it flame retardant, and the good chemical resistance that this material would present. And also the combination of those two structures will drive part of the other second set of properties that will be the very good barriers for water vapors and oxygens, and at the same time very low moisture or water absorption. With all of that, what can we do with LCP? So one of the part, it is definitely the high flow properties that this material will have. So to have an idea, we mold parts that are around 0.2 millimeters to below that level. So just to have a little bit of sense, it's pretty much like a molding if you get a A4 piece of paper, fold 4 times, it's pretty much that wall thickness that we can mold. So in certain cases are even below that, so 0.1 to 0.15, which would be like almost getting a stack of 2 A4 papers together. So this is give you a sense of how challenging those thicknesses are. The other part that we do, we combine this technology with a different type of fillers. So the same time that it is a super high flow material, it does allow us to add a lot of content inside. So we can develop formulations, as you can see on the picture to your right, that will address certain challenges that you may see in different parts. So one thing it is being able to model the part, and then the other part it is have a very homogeneous distribution of your content inside of those parts. And we'll talk more about in details about that. In terms of flowability, also we have on the chart on your left an example of the variety of different grades that we have been developing. So one part it is the evolution of the industry, keep pushing for smaller and smaller part. So if you think about connectors in the old computers to the laptops today or to our cell phones today, you can see how much the parts have decreased in terms of size. But at the same time, the amount of energy and the amount of a data that those small connectors are handling is still increasing. So we need to be able to keep the pace on that and then bring in new products to the market. Other things that we need to consider, and one part for overall cost, it is the use of regrinding. So LCP, very good material in terms of thermal stability. So it will allow us to use a very high content of a regrinding. Also, we'll touch base on that, but if we design the content, the tool in a very correct way, the runners engaged shouldn't take that much or shouldn't generate as much regrinding. But in case you do, we can make sure that this material can be used as a post regrinding material added to the original material. Another part it is make sure that we have very good moldability. So the dimensional stability part, the releasing part of those parts. So considering that most of those designs will be very complex, so we need to make sure that those formulations are very stable for moldability. So we take the advantage of the rheology of the material and then improve that towards the different formulations that we develop. One part that I think it is interesting about LCP, we always tend to think about LCP as the pellets for injection molding, but it can come in many different ways. So it can be used in a fiber format. So just you to have an idea, aramid fibers are also LCP-based fibers. It's just that it is a different family of LCP. It's what we would call lyotropic LCP. So the only way to make sure that you get that to become the aramid fibers is dissolving in certain solutions. The fiber that I have in my picture here, it is a thermotropic one that we use for spinning applications. And the other ways that we can use LCP is also in the soluble form. So you can see on the picture, the third picture here, LCP can come in a soluble way. So those are used for CCLs or flex films and in diaphragm for audio systems. So I'll touch base on that LCP has some very unique features that allows us to design and create new applications that we haven't thought before. And the final form that usually we drive to the market, it is on the powder form. So it can LCP can be used as an additive for metal coating technologies. So to get to that point, we have to develop a very unique set of LCP families that would be coming in the form of a powder and then can be added to the metal coating formulations. the majority of applications here are described on this slide here. So in automotive, we have applications that go under the hood and environments that the temperatures and the chemical resistance become super important. For audio system, I mentioned a little bit about the diaphragm applications, so we can generate some unique type of sounds and very clear sound systems. Datacom, we do apply a lot of the filler technology to develop dielectric modified grades, so very low dielectric constant materials and low dielectric loss materials that can address the needs for very high frequencies that are being demanded nowadays with the technology in terms of a radar system and in terms of a 5G technology antennas. For electronics, a lot of the high performance and then the data communication part of the devices. So a lot of those different type of connectors, different type of speakers, different type of antennas that goes inside of that. So LCP, one of the major markets, definitely on the electronic side. For office equipment, components for printers, for the projectors, anything that where you can imagine that will be exposed to very high levels of temperatures, LCP will be one of the major, I think, solutions behind. Similar case for kitchenware. So in this case, we can take advantage of the material being very, very thermally stable, not having a lot of gassing coming off the product, and then the possibility to expose those products to a very low temperature when you are having in the freezer, for example, and then move into the oven or microwave where you're going to expose those containers to a very high temperatures. So one part that I mentioned about LCP is the unique rheology behavior that it does have. When you see this chart to the left, the curve in black represented the amorphous material. So it is a material that you won't see a lot of the change around behavior when you increase the shear rate. So the viscosity will shift at the higher, super high levels of a shear, but it's not going to shift it that fast compared to an LCP. So LCP, in other words, would be a shear thinning material. Higher the shear level, lower the viscosity of this material. So if we look at that, how we can take advantage of that, when we are designing tools and runners, we can reduce the size of those walls and then generate a lot of a high level of shear in those cases, getting the material to flow really, really well. And then towards the end of the part, where the shear start to kind of being reduced because of the type of wall designs that you may have in those parts, the materials start to decrease in terms of flowability there. And to take that in consideration, then temperature is not the only factor or the only knob that you can use when you're doing injection molding of LCPs. On the chart to your right, you can understand that kind of behavior a little bit more on our grades. So different type of grades and different type of filler may translate into a different levels of of shear rates here and viscosity. But comparing to the traditional materials engineering thermoplastics, I mentioned in the beginning that this material have very low specific heat. So you have a super high flow material that tends to solidify way faster than any other engineering thermoplastic. So when you think about that, you can mold very complex design and not being concerned about the flash part or the freezing part of this material. And that's the kind of, I always discuss with the Sodick team about that it's the major advantage of the combination of LCPs and the Sodick equipment. So the injection molding machines that the Sodick have today, it does help us to generate very high precision measurement, high precision transfer rate of those high flow materials. So if you think about a machine that doesn't have a very good leakage system on the check rings or on the plunger side, you're dealing with a very high flow material. So a lot of this material may not be efficiently or precisely transferred to the cavity. And that's why, we work in partnership a lot with the Sodick group, because their equipment does allow us to take advantage of the behavior that the LCP has. So it's same kind of, if you have a, super sports car, you're not gonna use a normal gasoline there. You're gonna use the high octane gasoline. So to take advantage of the material, we need to think about many different points of this whole development chain. So one part it is the raw material, the other part it is the design of the part and the tooling side, and then the third part it is the processing equipment that you are using and how you are using it. So the combination of that will translate into success of your part development. We talk about high flow. So how high flow? So this chart gives a very good, I think, example of when compared to other polymers, where we are standing in terms of flowability. So this is a flow length tool, 1 millimeter wall thickness, which per what I've been describing so far, I would consider pretty thick part for LCP, but for the majority of the other polymers are kind of a very reasonable thickness that can be used for testing. So if you look at from the PPS standpoint, LCP will be about 2.5 to 3 times longer flow than a PPS. So which means if you're molding a certain size of part, your pressure to fill that part is going to be way, way, way less. Or in certain cases, you can reduce that wall thickness by half and still be able to mold that part. So it translates in a lot of different savings and a lot of different usage of the material that before, I think it was limited by the material flow capacity. So that's why, in many applications where you see very intrinsic designs or very complex components, we think about LCP as one of the major solutions for the applications. One thing is, I think it is molding thin parts. The other part, it is, are you going to be able to use that part the same way that initially was designed with a thicker part? So in other words, we'll have the similar mechanical behavior, So that's one of the key, I think, beauty about using LCP in very thin walls. You see on this chart, if you move to the left, you're going to a very thin part. And thinner the part, higher the tensile strength. So overall, the mechanical behavior LCP is going to be higher. And part of that it is because the behavior that the LCP has in terms of having the skin core effect of those parts. So on the right, you can see on the picture that the out layer side of the parts always going to have very high orientation. It is going to be what we kind of consider the skin layer part. And then the core, where you're going to have a little less organization. So the core skin ratio becomes very important to translate to mechanical benefit of LCP. Thinner the part, very oriented the skin is, higher the mechanical will be. So in other words, thinner parts, very robust parts, which in certain ways, when you're troubleshooting certain parts, you go towards the different direction. As an engineer myself, looking at certain parts that are cracking or breaking, the first reaction is see if you have a real estate to increase a little bit of the wall thickness. So you can put a little bit more material there and then make a little more stiffer part or stronger mechanically part. But in LCP, if you're troubleshooting, you need to think in a different concept here. If you had more material, you may not increase the mechanical part of that, that section of the part. So that's one of the major difference when you're looking to, traditional polymers, like, in this case, PES and PBT, where the overall performance is not going to shift that much and then tends to increase a little bit in certain cases. In LCP, that when you go thinner, your mechanical property is going to go better. The other part, it is make sure that, other characteristics of this component will hold the same. So in many cases, we always recommend to reduce the wall thickness of the part. So it's not just because make a huge, I think, business case in terms of a cost advantage, but also it's going to make it part more robust. But at the same time, when we recommended that, we do take a very good care of understanding and testing those concepts to validate that idea. So in this case, you can see that the electrical properties or isolation properties in terms of dielectric breakdown voltage increase with reduction of wall thickness. So again, with the evolution of the technologies and the need for miniaturization of components, LCP definitely become a very robust solution because you can make the part pretty strong in a very thin walls, and at the same time, very robust in terms of electrical properties. So you're going to thinner walls and still holding very good electrical, and in certain cases here, you can see that there is even an increase of performance for isolation. So which translates into very good news when you're designing your part. I mentioned a little bit about LCP as an isolating material. So I just want to kind of position that versus other polymers that can be used for similar applications. So in this chart, you can see that the LCP holds pretty good dielectric breakdown voltage characteristics, even compared to very traditional engineering thermoplastics. And the other good part it is we did some additional testing with SumikaSuper LCP in a variety of different temperatures, up to 200 degrees C. So even in those very stringent conditions, LCP does hold very good isolating properties, which makes it a very unique material to be positioned for electrical applications in electrical motors and battery components for EV or electrical vehicles developments. When we think about dimensional stability, the water absorption have a couple different factors here. If you think about the number one being dimensional part, materials like nylon, when it does absorb water or humidity, it tends to increase it in weight. So up to 5, 6, and even higher, depends on the condition. And this increase on weight will translate into variations of the dimensional stability of the part. The other part, it is, when you observe that part of humidity, it would affect some other properties. In the case of nylon, you're going to tend to get the more flexibility or higher elongation. So this water absorption will make the material a little less stiff. And in the case of LCP, as you can see in this chart, has very, very low levels of water absorption. So when you talk about the 0.02, it's extremely, extremely low. So that's a good news, because when you're thinking about the different applications, you don't want to have any dimensional shifting when those parts are exposed to different environments. So if you think about aerospace or automotive applications where it's going to be those components will be exposed to a very large different environments where you have very humid regions and very dry regions. You don't want your parts to behave and perform in a different way. So let's say that performs well under humid condition, but it cracks when it is in a dry condition. So that's translating a lot of other mechanical failure and a lot of concerns. So you want something that is extremely stable and holds that in many different ranges. Another component of the humidity is that it would affect your electrical properties. So this is just an example of the different tests that we did in-house. So you can see that even at a very high level, of up to 95% of relative humidity, LCP is still extremely stable. So that's the part of proving of a concept. One thing is understanding that the material does not absorb a lot of humidity, but the other part is how that would affect your overall properties. So that's why we take so much care when we do development to measure that in many different frequencies and many different conditions. So As you can see, dielectric constant and dielectric factor here, or dielectric loss, does not change with the humidity environment shifting here, which is very good news, because a lot of the applications that we would be using LCP, it depends on that, and then the electrical engineers depend on that design too. So if you have variations happening, it may throw you off or may get a different, results. And in certain cases, for example, in an antenna case, it can be the difference between have signal in one region or not have signal for your device. So very important property, and very good that we can deliver those stable conditions with LCP. And by the way, if it is there any interest to discuss even further, please let me know, and we can talk enough about different other sets of data that we have developed in-house, where we do test LCPs and SumikaSuper formulations at very high frequencies and many different temperature conditions, because that's the other factor that can affect the integrity of the signal and integrity of retention of those electrical properties. Staying on the dimensional stability side, CTE is the other part. So the coefficient of thermal expansion is another variable that may affect the performance of your part, especially when you're combining, plastic housings with metals, or plastic housings over circuit boards that have different levels of, behavior in terms of CTE. So the good news about LCP, very linear behavior, stay very, very stable in many different ranges of temperatures. So when you're designing your component, you can predict the behavior of that part in many different temperatures. It's something that, PPAs or PPS, in this case, you can see that has some kind of different variations. And that sometimes make a little difficult to you to design your component to perform well in a very broad range of temperatures. So that's one of the good part of LCP, almost an amorphous behavior here, and that's due to the crystalline structure that we discussed in the beginning, that has that very high organized structure of the rods that does kind of allow us to, deliver those type of properties. I mentioned in the beginning about certain properties that we are start to take more advantage on LCP side. So in terms of damping properties, when you are looking to something to absorb a vibration, usually you think about something softer. So rubber always gonna be very, very good for absorbing vibration. And metals, in the other axle here on the flexural models like aluminum here, will be very poor from that perspective. But at the same time, when you need something to be structural, metals way better than anything that is going to be softer. So that's the unique part where we sit with the LCP here. It is a material that has a very high modulus, so can deliver very high flexural modulus levels, but at the same time has one of the best, I think, behavior in terms of damping properties here. And on the chart to your right, you can understand how can we take advantage of that. So the attenuation of the vibration or attenuation of certain sounds is going to happen way faster and way cleaner than comparing to the other polymers. So for the applications in the audio system that I mentioned in the beginning of my presentation, that means that you can produce certain sounds and have a very fine definition of those sounds in a very, very unique fashion. So that's why LCB start to be extremely explored for application in very high-end audio systems being developed nowadays. Another property that LCP exceeds, it is on the water, vapor, and oxygen barrier properties. So it is something that in certain applications, I think it is one of the desirable behavior that a lot of companies are looking at. For example, in electronic packaging, for example, you want to protect the electronics that are embedded in those devices or in those housings. And LCP being a very good barrier for that, for water vapor or oxygen, will make sure that nothing kind of get inside those packages, and I would say, oxidize those contact points, especially if they're gonna be generating heat. So become a little more reactive from that perspective to those different environments. So LCP, very unique materials to those type of application. And at the same time, when I mentioned CCL, also one side it is the low dielectric constant that the LCP can drive, but the other part it is this barrier that can protect the metal layers that go below the plastic layer there. So with the LCP usage for those type of applications, we can drive some very unique properties to those needs or those attributes that are required for those different developments. One thing that I just want to touch base here pretty briefly, it is on the thermal conductivity. So for certain application, thermal conductivity, it is kind of important. So one thing that is very unique to the LCP is that throughout the molecule structure, the conductivity is extremely high compared to the transverse side. So that's why you see the translation to the chart on your right, that the conductivity to the flow direction is going to be extremely higher than at the transverse direction of the part. So in certain components and in certain applications, we can take advantage of that and design the components to be oriented in certain directions, and then creating those conditions that together with some additional filler can give you a more conductive design part. But at the same time, most of the parts, I think we can break that also and then be a little bit more in between those two layers, levels. So very unique part of LCP to get this understanding that the transverse and the flow direction, you're going to have a little bit more differences between conductivity levels. For the outgassing part, I think it's a very important understanding too. So the other polymers, in part, won't be very thermally stable to expose to very high temperatures. In LCP, it is, as I mentioned in the beginning, because of the chemical structure and the crystalline side, we can deliver very good thermal stability of those formulations. So once exposed to very high temperatures, we don't have a lot of things coming off of those formulations, which translate into, in certain cases, very good performance, molding, longer molding conditions without having to tear down your tooling for cleaning. And at the same time, those data will make sure that we have a formulation that can be used, for example, in conditions that are very, very unique in aerospace, where the level of components that comes off becomes super important, So LCP is one of the few materials that, can go through the ASTM E595 and deliver the necessary performance required by the aerospace. And one part, it is definitely for the low outgassing behavior. From the cost perspective, I mentioned a little bit about recycling. So when we mention about, you can use, 30%, 50%, 70%, we do take that very seriously, and then we run a lot of testing in-house. So those charts is to make it clear that, the thermal performance and the thermal behavior of LCP and the stability of those formulations can allow us to use a very high level of regrinding to the overall usage during injection molding. One part, I think, if you get us on board very earlier in your project, we can definitely guide you towards how to design the gates and runners and help you to optimize the size of those to not generate that high level of, post material. But in case, for certain different reasons that is not possible, we can do put those back to the processing and molding parts that will hold very good mechanics towards the end. Certain things I think it needs to be just mentioned here that certain cares needs to be put in place to make sure that we have a very good quality regrinding too. So in this slide, I mentioned a little bit about that, but if you want to discuss in more details, please, get in touch with me, and then I can get you some additional information about how to handle some of those materials for regrinding usage too. This is a very busy slide, but just to show, the large portfolio of products that we have, and this is not even cover all the different ones, but this is just to give an example here and show you that, we have many different series of products, and they are designed to deliver different thermal performances. So going from the 6000 HF series that it is processed about the 350 degrees C, up to the 5000 series that it is processed over 400 degrees C. And then we combine that to our filler technology. So this is to translate into solutions to our customer. And as I mentioned before, the type of parts and design of the parts have been shifting and changing with the needs for smaller and more complex design. In certain cases, with the increase of the number of pins, for example. So we have a lot of different challenges in terms of part designs and part concepts. And that's why we end up creating different grades, combining those different solutions to different type of family of resins. But another way to see that it is, looking to the attributes that you want to address or you want to drive. We can combine the different fillers and start from a very standard LCP with fiberglass, for example, 35% fiberglass, and then migrating to different type of attributes that you want to improve towards, certain designs. In certain cases, there's so much you can do in terms of a part design or tooling design, and then get back to the material side to do some changes on the formulations and adding certain components there that can improve a little bit towards certain attributes that are required by the application. So here you can see some examples here that for if we go to the left here and you need to improve flowability and mechanical part, we do have, for example, the E6808 UHF or E6808 LHF. And if you're looking just from the flowability perspective, you can go here on the bottom side of the chart for the FPC part, and then look into some of the very high flow, super high flow grades, like the SZ6505 or the SR2506. So this is, I would say don't get too hang on that. And if you need any help to look into the material solution side or the material selection side, please get us involved, and then we can make this kind of exercise for you. We'll ask you a bunch of different questions for sure, but we'll try our best to guide you towards this and then narrow down the type of materials that we can offer to your application. And when I talk about the material selection and the guideline about that, why, we are so kind of take that in high levels. So in this slide here, I think it is one of the critical points about, the importance of this discussion and the understanding of your application so we can develop better and better materials. One part it is, when you are using a high flow, in many cases, you may be able to be molding the part really, really well. So if you look at the pictures to your right, you can see that the part, if you look from the external side, it will look perfect part. But then you start to see cracking happening at the base of the connection points there, and you start to investigate what's going on there. And as you can see in the picture, the top part of the part pretty much don't have any filler there, and the bottom part you have a lot of strangulation happening there because of a lot of the fillers kind of blocking the passage to the thinner wall section there. So that will drive, this kind of very complex behavior of a warpage happening in this part and cracking happening on the base. So the top part not having a lot of filler will definitely see more shrinkage happening there. And the bottom part, very minimal amount. So for sure, you will see certain warpage behavior happening towards this part. The middle part, you can see similar kind of concept here, a little bit more filler going towards the top part of the part, but it's still not at the ideal condition that we would like to see. So, it is a step better than the picture to the right, but what we would like to see and what we take in consideration when we do development and we are having all those different type of grades is achieving what you're seeing to your left. So very homogeneous distribution of those fillers and all the different walls from the base to the top to the side walls. So that will give us a very good feeling about, this part will perform as it was designed. So in many cases, you see the part and you think that you're having a very well molded part, but what you can see when you do a little more analysis of that part is that certain challenges or certain issues that you're having in the part could be related to a little more kind of a basic concept there, that it is the formulation that you are using for that solution there. So for me, this is, I think, is a very key component that we can definitely help you to navigate and then help you to understand certain things that happen to your part. So in conclusion, I put an example here that we run with one of our automotive customer in an application for an under the hood component. So this was a opportunity that we have to analyze different materials and then that were taken consideration by this automotive customer to prove to them that, sometimes you need to be careful when you look just on the overall cost per kg or cost per pound. The first impact that you always gonna have is that, certain products are way more expensive than others, but I don't think that's the main part that you need to take, in consideration when you are analyzing a part. You need to look at the whole picture. And that's what this kind of slide tried to make it happen. So with the LCP, for sure, starting a little more kind of the high-end cost part compared to other engineering thermoplastics, not even compared to the high-performance plastics. But, we start with a delta in terms of pricing. But in this case, we were able to optimize the runner here. So we were able to reduce the dimensions and the size and reduce the overall, usage of material there. For me, this is kind of very critical because, material used in the runners are not materials that you're going to be able to, take it as a full part. So it does not translate any gain. So reducing that, definitely it is a major benefit for your project. And then the other component that will drive a lot of the different benefits or the gain on this project was related to the cycle time. So in the beginning, I mentioned about the behavior that LCP has in terms of solidifying really fast, being able to be molded extremely fast. So we are able to reduce the overall cycle time. The fact that the materials settle down super quick, it does translate into reduction of the cooling time. So compared to nylons or PPS, we can have a very, very fast, efficient cycle time here. And then when you do that, you have a major reduction of the cost per part. So you can see at the bottom part, we end up in the green. So we start in the red, but when you look into cost per part, that's where I think the most attention needs to be paid, because that's what you're going to pay, or that's what is going to cost you to get this part done. So this is, I think, is one of the key components behind when you are thinking about part optimization or considering different materials to be used for your project. And in this case here, we didn't even look into, or we didn't have a chance to look into change the cavity or the part design. So the runners was a very easy task to us to get it done. So it was a quick fix, a quick change, and we could prove the concept to our customer here. And the other part, when I mentioned about the cycle time, that translates in a lot of different savings. So considering that you can mold that in 2.5 to 3 times, less time than you are molding engineering thermoplastics or high performance plastics, that's translating a lot of savings in terms of number of parts produced. Or, for example, to be able to produce the same amount, you need to increase the cavitation for all those other polymers. And when you're doing or cutting a tool, the most expensive part, it is the cavities itself. So more cavities will translate into more cost. Also, make it the maintenance slower or more expensive, because that's the part that you need to be taking care of. So if you have more of those, you're going to have to take care of all of them. So increase the number also would require larger machine, because your framing will require to be a little larger and may not fit these smaller machines that usually we could process it to cavity parts there. So everything starts to translate into increasing overall cost there. And the other part, it is the amount of parts that you can produce in the same amount of time. So with the LCP, in this case, we could even reduce the number of shifts to produce the total amount of parts that you have to do it. So looking to this overall perspective, there is a lot of savings that can be achieved just from the cycle time perspective. The other part that I mentioned on the previous slide, it was that we didn't do the change on the cavity, but we did this study by ourselves, doing some modeling of those parts. And very rough estimation was that we could even reduce additional or create additional 30% savings just in terms of weighting of the part. So reducing all thickness, optimizing certain sections of the part. So overall, the gain, if we have started this project with LCP, could have done even larger, I think, gain to the end of this design of this project. But this is overall, just to give some example, this was just a case that we can we could participate with our customer and then do some kind of understanding of how the LCP can benefit your project. So this is kind of concludes my presentation today, and we can start to check if is there any questions or is there anything else that we can do to clarify certain points that I may not have addressed in my presentation.
Thanks, Edson.
Great. Thank you.
Great, yeah, I just great, one thing. Great job, Edson. There's so many things beneficial about this LCP. I mean, and we run a ton of it, obviously, but given the right the right equipment, the right certainly tooling is super important. Understanding the behavior of LCP. I mean, at times we're injecting 0.015 seconds, which is insane, right? But with 1/10 of a millimeter gates, right? Super small runners, to the point where, from a manufacturing standpoint, some of my customers, some of these big companies are trying to understand what other part numbers can they make out of LCP. Just yet maybe it might be a little bit more expensive or something like that. But from a manufacturing standpoint, again, given the right tooling and everything else, it's got to be all good. But I got maybe a 4-cavity cold runner can outproduce, say, a 16-cavity hot runner.
Correct.
Big molds, small parts is very common out there right now, and we're showing that with these super fast, especially for some of the small connectors and things like that, some of these super fast molds. Of course, the machines, we're 2.5-3 second cycle is not uncommon.
That's
So
true.
you might, even if replacing materials to LCP makes sense on the manufacturing side, just
Correct.
how quickly, like you said, no cooling time, you're
Pretty
injecting
much.
it super fast and it's over, so anyway,
And I think then this is one of the key messages that I try to get in the final stage of those slides is that, don't look into the overall cost per kg because that doesn't translate directly to your part. So the benefits that certain materials has, it's very unique to, LCP in this case, and can translate in a lot of gain in terms of cost per part. So in the end of the day, that's what the main thing that, if you take it from this presentation is what you need to pay attention. So if you can produce the same part with less cost in a very efficient, very precise way, that's what we want to do it. So that's what we are always trying to help our customers and interfacing with, company like yours to make sure that we drive products that can address that. So
absolutely, just let us know offline or whatever if we could. Anybody out there needs any recommendations or things of that nature, would be happy to. We're kind of an open book. So
yeah, and again, to your point, 0.3 to 3 seconds is the normal. In my example, I was using very high cycle time because the part is pretty big. But in this case, it's very unique for LCP because we didn't have a chance to optimize the part. But I'm pretty sure that if we could optimize the part together with the runner combination that we did, we could have made a major strike in terms of saving on that part.
For sure. Awesome. All right, I'll sign for now. Thank you.
Thank you.
Thank you, Len. Edson, we did have a few questions coming in here.
Okay.
So the CP withstand soldering temperatures?
Oh yeah, I didn't mention that, but a lot of our products are designed to be used in SMT conditions. So when we do the formulations, we make sure that they are designed and they are tested to be able to handle the soldering conditions there. I lost you for a moment, but just saw that you came back. But yeah, no, they are all tested, all designed, and the thermal performance LCP does allow us to hold the dimensional part under those conditions for sure.
Excellent. You can hear me okay, Edson?
Yeah, I can.
Okay. Are the materials approved for medical use, for bio approval?
So we are working on that part, and right now, the major focus from our organization has been on the electronic side, and then now we are taking this knowledge to different frontiers. So we're spending a little more time, and we are working with that right now in the US, Europe, and Asia. So in pretty soon, we're going to be able to start to be more active in this market for sure, in the medical market.
Excellent. Is LCP a high temperature material? Does it require special molding equipment?
No, it doesn't. That's the other beauty about LCP. We can use a water cooling system or water running system with no any special metals on that, and it will perform in the same way. Comparing to certain nylon formulations or certain PPS formulation that does require oil or pressurized water system to create the heat there. LCP does not require anything special. We can mold those parts in a very standard systems and then getting the parts, to perform in the way that it needs to perform.
Wonderful. So why does LCP require higher mold temps, even though it is high?
It does not require high mold temps. Depends on the applications where you have a little more high precision parts. You want to make sure that everything in terms of post shrinkage or any stress is released during the molding process. So certain applications, even if you want to get a better surface quality, so if you want to record better the tooling surface, you may use high temperature tools, but it's not required. Usually, 70 degrees to 80 degrees C, it's more than enough to get the LCP molded.
Excellent. Now, a lot of our listeners probably use regrind, and What's the maximum amount of regrind that can be used?
Okay, so regrind is one of those that I think we need to take in consideration what the part that you're producing. So how critical are those components? How many features, are critical to that application? So certain dimensionals or certain mechanical part. So that will probably define better the amount that you can add. But from the regulatory standpoint, we test our materials under the UL conditions. So make sure that when we recommend, in couple of our formulations, 70%, that the material is still holding the flammability levels that is required by UL, and does hold all the mechanicals that needs to address that. So I would say in very critical conditions, we can use up to 70% in certain formulations. So for example, E6007 LHF. But in general, I think if we get involved and we help you to design the part and the tool, I don't think we're going to generate that level of a regrind. 30% or 20%, pretty reasonable to see it around. But 50 to 70, extremely cases that probably we can definitely help on in case you need to optimize those situations.
Wonderful. Can LCP withstand 2 to 4 atmospheric pressure?
2 to 4 atmospheric pressure. You're thinking about barriers?
That we will we'll see if they can elaborate a little bit on that atmospheric pressure question.
Yeah.
We'll give them a minute there. We'll move on to the next question here. And how is the knit line strength, and how do you characterize it?
Yeah, so that's one of the challenges in LCP. The fact that the material settle down super quick, it would generate certain areas that the material, it's too, I would say, solid to get a very good interfacing for welding line. What we do is taking in consideration the part design and try to get those welding lines to areas that are not going to be under extremely loading or critical to the application performance. So that's why it's important to get us involved right at the beginning of the project, so we can spend the time and then guide you towards some of those considerations that needs to be put in place to validate that. There are a couple of different other features that we can play around, but most of the time, the welding lines will be there in certain cases, and we'll have to position in a way that is not going to affect your part performance.
Have you seen success in rotomolding LCPs?
We start to do a little bit more investigation towards that. So we have certain products, like I mentioned to you, that can be in different shapes and forms. So just initial assessment of that, we are partnering with a couple of different organizations and companies and doing an assessment of that. It's a very unique process for LCP. So the learning curve is pretty steep. So I would say that we have success, but we are working on that right now, I would say.
Wonderful. We'll give a few more minutes here, Edson. That's the end of the questions for now, but we'll give a few more minutes. If there's anything else out there you guys would like to ask, send them over and we'll get Edson to answer these before he jumps off here.
And by the way, I have on the screen here the contact. So this is our team here in the US. We have Hiroyasu Yamauchi. It's my partner on the LCP side, and we support a lot of the applications and a lot of the technical needs or questions. And Janice Griswold that help us on the PES and also in LCP. She also has a huge background in thermoplastic and can help us to address some of the questions. So anytime if you want to get in touch with us, feel free to use one of those channels here. And if you have more questions, more specific, today my goal was to get the high level understanding of LCP, why it behaves the way that behaves, and what drives the initial understanding of LCP. But if you need additional information about a little more specific conditions, like I was mentioning about, formulations that may have a little more this specific design for electrical properties in case of very low decay grades. Get in touch with us. We will definitely help you to navigate to that part.
Wonderful. Question just came in here. Waited just long enough. That's it. Is the material characterized by mold filling analysis?
Yes. So a lot of the formulations, when we do the development, we work with the mold flow organization to get them characterized for simulations. So a lot of those products, if you're considering certain new formulations, may not be as a public domain. So get in touch with us and we can work that part to get to the specific files for the simulation software's cases. Yes.
Wonderful. Wonderful. Now, does the mold flow properly simulate the shear sensitivity of the material?
I would say lately it's getting better, and I think our understanding of how combining the software technology to the LCP behavior is getting better also. So this combination, I think, is driving a little more accuracy to those simulations. But it's still a lot of this. I think you still rely on people like us to guide you towards the understanding of those results. So do the simulations one part to make sure that you have some validation about those analyses. I think are extremely important. The software definitely is designed for more semi-crystalline materials and traditional polymers. So LCP, like you saw in the presentation, is very unique. So it does take certain, I would say, setups and the boundary conditions that can definitely translate into very good results. Yes.
Excellent.
But the best simulation tool is still having a prototype cavity. But sometimes, certain project doesn't allow that. But
excellent. That brings just questions here. I'd like to say thank you, Edson, for joining. What a great presentation today. On behalf of Len Hampton, Bennett, Howard, who had to step out, and myself here at Sodick Plus Tech, thank you everybody that joined us, sat through, and learned from Edson here today. So with that, have a great day, and
thank you very much.
Great job, Edson. Thanks so much.
Thank you, guys. Thank you very much.
Okay, take care.
Take care. Bye now.